Good afternoon, ladies and gentlemen. This picture was taken by WWF in Norway, showing one cob jellyfish floating in the water and another of some crabs on the seabed. Comb jellyfish are amongst many species that are typically sucked in as ballast water for ships. The catastrophic ongoing impact of untreated ballast water on marine ecosystems forced the environmentalists to call the ballast water as the second biggest threat to global biodiversity after climate change. I will pass fast the next slides as have been shown by the previous speakers. This is the modified scheme of IMO MEPC 65, and there are two major changes in this scheme. The spread of retrofitting of BWTS systems to the existing vessels is now 5 years instead of 3, and for the vessels built on or after 2012, the implementation is transferred to the first renewal survey after entry into force. However, on the other side of the Atlantics, the US are moving faster. This is the final rule of the US Coast Guard, which specifies also the discharge limits of the ballast water within US waters. However, looking at this table, we can point out that there is an issue, and this issue is the harmonization issue. The harmonization of IMO schedule with US Coast Guard time schedule. For example, a vessel with dry docking within 2016, simultaneously with intermediate survey, as per revised IMO time schedule, is not required to install a BWTS system. However, in order to comply with US Coast Guard time schedule, is obliged to do so. The US Environmental Protection Agency, the EPA, issued a final vessel general permit, VGP, regulating discharges from commercial vessels, including ballast water. This entered into force on 19 December 2013. This final VGP regulates actually 26 specific discharge categories and contains new numeric ballast water discharge limits. The VGP applies to most vessels trading in US waters, and each vessel has to document that it fulfills the requirement stated in the VGP. The VG requirement issued by the EPA generally align with the US Coast Guard requirements. However, the VGP contains some additional requirements to ensure that the systems are functioning properly, for example, calibration of sensors, sampling, etc. The implementation schedules of EPA, VGP, and US Coast Guard are identical. There are 4 options for compliance. Either no ballast water discharge, or a vessel has to meet discharge standards by using a US Coast Guard approved AMS. As already mentioned, the US Coast Guard allows the temporary use of AMS, alternate management system. A third alternative could be the discharge either to another vessel or to an offshore facility for further treatment. And the last option is to use the most expensive one, to use only water from a US or a Canada public water system. Recently, IMO Secretary General Mr. Sekimizu said that there is a good number of ballast water technologies now approved and available together with a fixed deadlines for their application. Looking at this table, we have to point out that some systems do not employ physical methods, whilst some other systems employ a combination of methods, and finally, some systems do not employ a supplementary treatment. However, we have to mention the lack of a quick sampling and analysis method for the treated ballast water. The pod state control sampling and analysis technique is very expensive, time-consuming, requiring special equipment and highly trained personnel. Complexity of retrofitting. The retrofitting of a BWTS system in existing vessels can be a far more complicated process than is apparent at first sight. There is a gray area concerning the engineering requirements and ultimately cost. With many vessels having very limited space, free space in the engine room, ship owners may find that they need to suffer a loss of cargo capacity or convention of a void space to accommodate the system. This would require updates of the trim and stability booklet. To complicate matters further, The overall footprint does not take into account the operation, the maintenance envelope, and with some internal components, such as delicate UV lamps, measuring many times over 1 meter in length. This can add substantially to the operational footprint. Even the grant error type approval does not guarantee that the system will be efficient for a specific vessel. For many vessels, the quoted pressure drop alone can constitute a requirement for larger ballast pumps to avoid a drop in capacity. Some vessels may need to alter their generator setup in port to account for the additional consumption. Switching from 2 generators on medium load to 3 on low load is not normally a huge problem. However, with increasing fuel costs and strict legislation on emissions, ship owners are interested to avoid running an extra generator in port. Perhaps the most critical aspect of the retrofit process is the planning and execution of the maintenance. In case there is no access to the desired location in the machinery space from the main deck, the ability to load large components of a BWT system becomes complicated and expensive. In these cases, a vessel may need to be dry docked with access holes cut on the side shell to facilitate loading of the system components. This not only complicates the retrofit, but increases dramatically the cost. In many instances, the quoted cost of the system itself represents as little as 50% of the overall retrofit cost, simply due to the complexity of the engineering required. We see here that for the retrofitting cost, we have to take into account the equipment cost, the retrofit cost, and the eventual off-hire cost. Summarizing all above, the selection of the most appropriate BWTS system is a complicated balancing act of cost, functionality, and retrofit complexity. Benefits for timely fitting. There are many considerable benefits for the companies in moving ahead. The crew training is very important because a detailed reporting will be necessary, as well as a familiarization with the operation of the system, the many onboard sensors, the data logging, the maintenance procedure. The crew can get operational experience before the port state control commences. Owners can benefit from a shorter delivery time of the ballast water treatment equipment thanks to availability, thus avoiding delays affecting the operation of the vessels. They can also plan the retrofit to coincide with a scheduled survey, avoiding additional off-hire costs. There will be enough time for better negotiations, obtaining lower prices. As sediments from spaces designated to carry ballast water will have to be cleaned, adequate time will be available for the selection of suitable port for cleaning or disposal of sediments and eventual repairs. The international transporters will only charter the most well-equipped vessels operating in the shipping market, and there will be better chances for a long-term charter. Delays of the classification drawings, which can be delivered at the right time, can be avoided. The thousands of vessels needed to be retrofitted within a short time, once the BWTS convention comes in force, will create a bottleneck at the yards with many side effects. Finally, there will be enough time for a techno-economical study that matches the requirements of the vessel's operator, avoiding a forced decision. Also, in case of retrofitting, a 3D laser scanning can take place to investigate possible locations for installation. Selection criteria. In case a system retains the original design, this is a good sign of the operation efficacy. We have to point out that some manufacturers have changed the operation principle over time. There is no certainty that AMS accepted systems will get the US Coast Guard type approval. The discharge must meet numeric standards, and the monitoring of compliance will occur. The selected system has to have a potential for better performance, as we expect stricter standards for US Coast Guard Phase 2. The systems which do not demand big changes of ballast lines present a certain advantage in retrofitting against other systems. Also, there are some systems which do not require dry dock or a yard's assistance and can be fitted en route. A confirmation of compliance with the PSPC requirements of the paints applied for the coating of the ballast tank has to be provided. This has also to be applied to various fittings, piping, seals, and valves. The robustness of construction, the reliability of the system components must include sufficient monitoring with many safety features for crew in the engine room. Handling of chemicals is of paramount importance, which also create additional logistic problems. The possibility of gravity stripping operation can be considered as assets for a system. The cost of consumables and the supply chain have to be taken also into consideration for the operation cost. And finally, the ship owners have to demand a comprehensive worldwide after-sales support. The MEPC 63 INF dated 1st December 2011, which was submitted by the International Paint and Printing Council, has examined the compatibility between ballast water management systems and the coatings of the ballast tanks. They came to the conclusion that for systems that work with chemicals such as electrolysis systems, chlorine dioxide, sodium hypochloride, peroxyacetic acid, or ozone in maximum concentration up to 8 milligrams per liter in treated ballast water entering the ballast tanks do not pose a detrimental effect on most coating systems. Therefore, they recommend as maximum limit, this is the TRC, the total residual chlorine, the 8 milligrams per liter for systems using only chlorine as an active substance. And here we come to the test results. Regrowth issue or avoidance of recolonization. Although IMO specifies 4 days for no regrowth in the ballast tanks, there are some companies which have carried out their own tests for more days. In this slide, we can see the results from laboratory experiments study growth of organisms in untreated fresh water and treated fresh water during storage from 1 or 20 days in simulating ballast tank. On the top left table, we see the organism concentration in effluent test water, here. On the bottom table, we see the viable organisms of the discharged treated water, which are 0. The question is for how long this 0 is kept. Finally, on the right table, we see the regrowth performance over time. There is no regrowth for 20 days. The most important out of the selection criteria is the actual test result. This is the moment of truth. The ship owners have to verify the claims of the BWTS Vento. The motto should be, show me the data. Does the system comply with the D2 standards, or the ship owner has to replace it with another system? The answer to this question is to attend a test in order to check the compliance. In this slide on the left table, we see the viable organism concentrations in effluent ballast water, and on the right table, we see here the concentration of viable organisms in treated water. It is clear that this particular system is scoring well, in fact, much better than the present D2 standard. Conclusions. Clearly, the BWTS installation is a very complicated issue. As mentioned before, there are many benefits for timely installation. In order to avoid future problems, it is strongly recommended to select such a system which scores better than the present IMO D2 standards, as we expect stricter rules for the Phase 2 US Coast Guard. Don't forget that's a rule-driven item. In addition, there are already fixed dates by the US Coast Guard, and the entry into force by IMO is just around the corner. Thank you for your attention.